Welcome to Lecture 5.3, the transport and wave equations. We've already seen the heat equation, which is a common one-dimensional PDE, ut equals c squared uxx. In this lecture, we will introduce the transport equation, from which we will derive the wave equation, which is another common one-dimensional PDE. The only difference is that it has an extra time derivative here, utt equals c squared uxx. We're going to start with a very simple PDE involving a function u of x and t. So du dt minus c times du dx equals 0. I've written it this fancy way instead of the much simpler ut minus cux equals 0 because I want to remind you that you can write this as a differential operator, d dt minus c d dx applied to u equals 0. So solutions to this PDE are precisely those things in the kernel of the differential operator. And I want to show you what those functions look like. So let's suppose that f of x is any differentiable function. So let's draw one. Let's think of it like a signal. I guess I didn't really draw to be very differentiable here because there's a corner, but let's pretend that that is, if you zoom in enough, it's secretly smoothed out, so it is differentiable. Now I want to define a new function of two variables, u of x t, which is f of x plus ct. Okay, so here's what that looks like. First of all, at t equals 0, then u of x0 equals f of x plus 0. So f of x, because t equals 0. So at t equals 0, our function is just f of x. Now at t equals, say, t naught, then I claim that the function is just a shift of that. So if this is negative c t naught, then notice that u of x t naught equals f of x plus c t naught. So in other words, this function of two variables that we've defined right here can be thought of as a traveling wave, where f of x is the wave. And this is traveling left at speed or velocity c. So I'm going to say that this is a traveling wave left at speed c. And I claim that this is precisely what satisfies or solves this PDE. And let's check that. Let's take the partial derivatives, du dt and du dx. So to do that, we need the chain rule. So recall how to do that. By the chain rule, if you're rusty on this, that's fine. Ut is the plain old derivative of this one variable function, f prime of x plus ct, times the derivative, the partial derivative, dt, of the inside x plus ct. And so that's just equal to c times f prime of x plus ct. Similarly, ux, the x partial, is f prime of x plus ct times d dx of x plus ct, which is just, now this obviously is 1, and so this is simply f prime of x plus ct. So now note that this clearly satisfies the PDE because the t derivative is c times f prime minus c times the x derivative. So the c times this minus that equals 0. Let me just write that down. So ut minus c ux equals c times f prime of x plus ct minus c times f prime of x plus ct. So yes, for any signal or any function f of x, if we turn that into a traveling wave left at speed c, that will satisfy the simple PDE ut equals c ux equals 0. So this is sometimes called the transport equation. Our next example is very similar to the previous one, except now we have a plus here instead of a minus. So this is the PDE ut plus c ux equals 0, or we can write it as d dt plus c d dx, this operator applied to u equals 0, and we're looking for the kernel of this differential operator right here. So as before, I'm going to let's call it g of x now be any one variable differentiable function. And let me sketch this. I'm going to make it a little bit different. Let me make it curved, like bell-shaped. And now let's define a function in two variables, u of xt. So think of this as like a movie of this function. So we're going to have this way, but we're going to move it now to the right. So this is g of x minus ct. And think of this as a traveling wave right at speed c. Okay, let me circle this or box it. So it's easy to check using the chain rule that ut is just g prime of x minus ct times d dt of x minus ct, which is negative c times g prime of x minus ct, and that ux equals g prime of x minus ct times d dx of x minus ct, which is 1 times g prime of x minus ct. So clearly, if you take ut plus cux, so if you take this guy plus c times this, you clearly get 0. So this is negative c g prime of x minus ct plus c times g prime of x minus ct. That's equal to 0. So the picture of this is that this is what it might look like at time equals 0. So this is u of x 0 equals g of x, and then at time ct, so here's ct out here, this is the u of x t, I should say at time t and distance ct, there we go, that's equal to g of x minus ct. And this is moving at speed c. Our third example has elements of the first two that are put together. So consider the following PDE involving a function u of x and t. So let me box this right here and write this as utt minus c squared uxx equals 0. So this is like the heat equation, but now we have two t's instead of one. Now I can factor this as the product of these differential operators. This is the one from example 1, this is the one from example 2. In other words, this is transport left, if you recall, and this one here is transport right. And so if we multiply these things together, you get difference of squares. So this is equal to d squared dt squared minus c squared d dx squared. So it's this differential operator applied to u equals 0. So what's in the kernel of this differential operator? Well, it's things that are in the kernel of this one or in the kernel of this one. In other words, we take this function and we apply it, or we apply this differential operator to it, and then we apply that one. So if either of these guys kills u, then u is in the kernel of this. So I'm going to now define f of x and g of x be one variable functions. And I'm now going to define u of x t to be f of x plus ct plus g of x minus ct. So we're going to take two functions and we're going to send one of them to the left and one of them to the right. And it's easy to check. I'll have you do this as an exercise, that this function u of t is a solution to, let me put a star here, to this PDE, which we call the wave equation. Let me box this so you can see this. Okay, so any function that has components that move left and move right, any sum or linear combination of traveling waves is going to be in the kernel of this differential operator. And now let me give you an initial value problem. So consider the following initial value problem. So let's take this PDE, utt equals c squared uxx. Let's suppose that the initial wave, u of x0 equals, say, f of x, and ut of x0 is 0. So this means that f of x is the initial displacement of the wave. Let me write that down. So this here is the wave equation. That's the name of this PDE that's above. F of x is the initial displacement. And 0 is the initial velocity. So picture like taking a rubber band. Let me draw this down here. So picture taking a rubber band and stretching it and then letting it go. So what do you think is going to happen, just purely intuitively, if you do this? This is a long stretch of rubber. You pluck it, you let it go. Well, half of the energy is going to go to the left and half of it's going to go to the right. And it turns out that what happens is, let me write this out, and I'll write it out and then I'll show you why it's true. So if you take half of this wave and you send it to the right, f of x minus ct, and this thing goes here at speed c, and then half of it goes to the left. So this is 1/2 f of x plus ct. So I claim that, let me first of all write ct here and negative ct here. I claim that the solution to this initial value problem at time t, so this is f of x, which is u of x and 0. But if you look at u of xt, I claim that this is equal to, or maybe I should not have boxed that. Let's undo that. This is equal to 1, basically this plus that. So 1/2 f of x plus ct plus 1/2 f of x minus ct. So let me write that up here. So I claim that the solution to this initial value problem is u of xt equals 1/2 f of x plus ct plus 1/2 f of x minus ct. Let me box that, and let's just go through why that is. So if you apply this differential operator to this sum, then, well, the transport right is going to kill this term, and the transport left is going to kill that term. The initial displacement, if you plug in 0 into here, you get 1/2 f of x plus 1/2 f of x, you get f of x. So this satisfies the wave equation, it satisfies initial displacement, and it's easy to check that it satisfies the initial velocity. If you take the, let's just check that, if you take the derivative with respect to t, what do you get? You get 1/2 f prime of x plus ct times the derivative with respect to t, which is c, plus 1/2 f of x prime of f minus ct times the derivative with respect to t, which is negative c, and you get 0. So yes, this in fact solves this initial value problem, and it completely matches our intuition as well. If you pluck this, if you have a wave here, suppose this is a long string of rubber and you let go, half of the energy will go left and half of it will go right. So the thing I want you to remember from this slide is this is the wave equation, and it comes from the transport equation like this. Let's summarize what we've done so far in this section. If u is a function of position and time, then the heat equation is the PDE ut equals c squared uxx, and the wave equation is the PDE utt equals c squared uxx. And finally, the title of this slide suggests that there are 3 common 2-variable PDEs. And we haven't seen the third one yet, and it usually arises when the 2 variables are position x and y rather than x and t. So suppose x is a function of position x and y, then Laplace's equation is the PDE uxx plus uyy equals 0. We'll talk more about this in the section of higher dimensional PDEs, but this comes up all the time, and we'll explain what this means physically. The examples that we've seen so far with the wave equation all involve infinite strings, traveling waves. Now we want to impose boundary conditions to model things like a vibrating guitar string. So I'm calling this example 3. I know we just had examples 1, 2, and 3, but this is referring to a different numbering system. In previous lectures, we looked at examples 1a, 1b, 1c, and example 2, and now this is the third one in continuation with that. Okay, so we want to solve the following boundary and initial value problem for the wave equation. So this is the wave equation, utt equals c squared uxx, and now we want to impose 2 boundary conditions. What this says is that the displacement at the left endpoint and the right endpoint, x equals L, are held fixed at 0 for all time t. These are initial conditions. This says that the initial displacement is the parabola x times L minus x, and the initial velocity is equal to 1. So here's what you should think about. So you should imagine a bar of length L, so this is x equals 0, and this is x equals L. And the initial wave is a parabola, and the initial velocity, so instead of stretching this, picture this as like a guitar string, and you stretch it up here, instead of letting it go, that would be the initial velocity is 0, it's being shoved upwards at unit velocity, like this. So this is the initial value problem. Notice that we have 2 time derivatives now, so now we need 2 initial conditions. It's like when we were dropping a ball off of the roof in basic calculus problems, when we had 2 derivatives and we needed not just initial position of the ball, but initial velocity. Were we letting it go, or were we throwing it up or down? Okay, so we will solve this exactly as before. Let me just write up that these are boundary conditions, and this is an initial condition, and this is an initial condition. Okay, so as before, we will assume that this solution separates. We are always going to solve these using separation of variables. And these boundary conditions, that should be f of x, g of t. So these boundary conditions are homogeneous. You could, in theory, add Neumann boundary conditions, but those don't have as much physical meaning. Because when we're talking about vibrating strings, it makes sense to hold the displacement fixed at the endpoints. It doesn't really make sense to hold the flux or have mixed boundary conditions. So this is pretty much the only boundary condition that we're ever going to see with the wave equation. Maybe that's one reason why it's perhaps, that's one advantage to the wave equation, is that the boundary conditions are easy. Okay, so let's take derivatives. So t equals f of x times g double prime of t, uxx equals f double prime of x times g of t. So let's use the 0 boundary conditions. So the 0 boundary conditions, let's use those. The first one is u of 0t equals f of 0 g of t equals 0. And that tells us that f of 0 equals 0. again, we have a number times a function being 0. That number has to be equal to 0. Next, we have u of L, and t is f of L, g of t equals 0. We have a function in time that's non-zero and a number equaling 0. That tells us that, that the number f of L equals 0. Okay, so now let's plug these back in. So we're going to plug, so as before, we're going to plug the derivatives into the PDE and separate variables, and then we will use these boundary conditions right here. So we plug this back in. UTT is f times g double prime equals c squared. UXX is f double prime times g. So let's do what we always do. Divide both sides by c squared fg and c squared fg. And if we do that, well, what cancels? So the f's cancel as before, and then the other side, the g's cancel and the c squareds cancel. So now we get that g double prime over c squared g equals f double prime over f. So the left-hand side is a function of time, meaning it does not depend on position. And the right-hand side is a function of position. It does not depend on time. So whatever this quantity is, it doesn't depend on position or on time, so it better be equal to a constant. So let's call that negative lambda. Okay, so we get two differential equations. Let's write these down. So we get f double prime. So let me box this. I think I'm going to leave a little bit of room because I'm going to write what the lambda is equal to. So f double prime equals negative f, or lambda f, and now we have these two boundary conditions over here. So we have f of 0 equals f of L equals 0. And then we have, so this is a Sturm-Liouville equation. It's a boundary value problem. And now we have g double prime equals negative c squared lambda g. And if we had a 0 initial condition, we could add that right here. So for example, if this were equal to 1 or 0 instead of 1, we could then say that let me write that. If utx0 equals 0, then we could say that ut of x0 is f of x g prime of 0 equals 0, and we could conclude that g prime of 0 equals 0. But that's not the case, so we can't do that. But if you have a homework question and one of these things happens to be 0, do that first. You don't have to, but it'll make your life easier. Okay, so we know how to solve these. This first one we are very familiar with. Again, if you have not watched the lecture on boundary value problems, please do that. So we know that lambda equals n pi over L quantity squared. We know that Fn equals, what is it? It's sine of n pi x over L. So let me box that. So negative lambda here, if you prefer, is negative n pi over L quantity squared. Okay, so that's what Fn, I didn't write, of x is. I guess you don't really need to. And now what is g? Well, actually let me undo what I just typed because I'm going to write this as negative c n pi over L quantity squared times g. So I'm just going to stick the c squared in here. And now this g double prime equals a negative constant squared times g. What's the solution to that, ODE? Well, that's also sines and cosines. So g of t, this is something you should be able to do in your head. G double prime equals negative k squared g. You know that g of t equals a cosine of kt plus b sine of kt. So g of t equals, I'm going to say a cosine of cn pi x over L plus b times sine of cn pi x over L. It's much easier when L is equal to pi here, because then these pi's cancel and things just simplify. Okay, so that's g of t. All right, and let me call this gn of t, because it's for a particular n. So now what we have is we have a solution. So for each n, so what about n equals 0? Do we get it? If n equals 0, then this is 0, so we don't get anything. So for each n, 1, 2, 3, etc., we have a solution un of xt equals fn of x times gn of t. And that's equal to sine of n pi x over L times a, I'm going to call this an and this bn. Actually, let me call, oh yeah, I'll put it in there. So an cosine of cn pi x over L plus bn sine of cn pi x over L. So that is our solution for each n. So that's our fundamental node. So now our general solution is u of xt equals the infinite sum from n equals 1 to infinity of, let me write this as, so basically we want linear combinations of these solutions. So I'm going to write this as, how about cn un of xt? Although there's really two constants buried in here, so I think the best way to write this is the sum from n equals 1 to infinity of, how about sine of n pi x over L times, I'm going to make these lowercase just to match what we do with Fourier series, an cosine of n pi of cn pi x over L plus bn sine of cn pi x over L. So that is our general solution to this boundary value problem for the wave equation. So this describes all solutions to the wave equation on a string of length L, given the fact that the endpoints are fixed at 0. I have done nothing with specifying either the initial displacement or the initial velocity. At this point, no matter what I make the initial displacement or velocity, I can make it a triangular wave or something like this that's squiggly, or I can realize that by selecting the correct A and B. So in the next slide, we are going to plug in the initial conditions and figure out what A and B are. So it's really the same process as we've done before for the heat equation. Nothing new. There's just two of them instead of one. We ran out of room on the previous slide, but what we did is we found the general solution to the following boundary value problem for the wave equation, and that's this PDE right here, utt equals c squared uxx, and these two boundary conditions. Together this represents all possible waves on a string or wire of length L, so this is x equals 0, x equals L, given the fact that the endpoints have to be fixed. And that is this infinite sum of an cosine of cn pi t over L plus bn sine of cn pi t over L times sine of n pi x over L. Now we'll solve the remaining initial value problem. So if we specify the initial wave, which is this parabola right here, that will tell us some information about the ANs and the BNs. In fact, that, as we'll see, that'll tell us what the ANs are. And then if we specify the initial velocity, which in this case is 1, so we're pushing the string upwards, constant velocity initially, then that will tell us what the b ends are. Okay, so let's do this. It's how we always do it. We just plug in 0 and we set them equal. So u of x 0. So what happens if we plug 0 into this big equation? Well, what goes away? So the sine term turns into 0, and we get an cosine times, no, actually we get an cosine of 0, which is 1 times sine. So we get the infinite sum from n equals 1 to infinity of an sine of n pi x over L. Does it look weird to anyone else that we have an an sine? Those don't usually go together. Okay, maybe it's just me. So we set this equal to the initial condition, which is x times L minus x. And this is a Fourier. So we have to write as a Fourier sine series. Because again, that function is just, that's this guy. So we have to write it like that. And so that is sum from n equals 1. We've done this before, so I'm not going to redo it. This is 4 times, what's the best way to write it? Well, how about if I don't write? How about if I write it like 4 times L over pi n quantity cubed, I think that's right, times 1 minus negative 1 to the n, times sine of n pi x over L. Okay, so if this sine series equals that sine series, then an better equal this guy here, 4 times L over pi n quantity cubed, 1 minus negative 1 to the n. So these things better be equal. Okay, next we need to use this initial condition. So to do that, we take the time derivative and then plug in t equals 0. So let's first compute the time derivative. We might be able to do this all at once, but it's easy to make a mistake. So ut of x and t, so let's take the derivative of this guy with respect to t. So that's n equals 1 to infinity of, okay, how do we want to arrange these coefficients? So we have, so we have an c times n times pi over L times sine of cn pi t over L. I know we have a negative sign here because we're taking the derivative of cosine. And now we have plus bn cn pi over L times cosine of cn pi t over L. I know this looks messy. I'm sorry about that. Not really. Times sine of n pi x over L. Okay, now let's plug in 0. So ut of x and 0, it gets easier, trust me. So you plug in from n equals 1 to infinity, what happens? So the sine term goes away. The cosine term becomes 1, and we just get this term here. So we get this thing times sine. So this is bn cn pi over L. And then what else do we have? We have a sine of n pi x over L. And we have to set this equal to what? To 1. Well, how do we do that? Well, we also have to set 1 as a Fourier sine series. So remember what that looks like? So we have the function that's defined to be 1 on 0 to L. So to write this as a sum of sine waves, we have to compute the Fourier sine series. So we compute the odd extension. So make it odd, make it periodic, and compute the Fourier series of that guy. So we've also done this before in the past, so I'm not going to redo it. But what this ends up being is so n equals 1 to infinity of 2 times 1 minus negative 1 to the n over pi, n pi times sine of n pi x over L. Okay, so just to remind you, this thing here, this is the Fourier sine series of x L minus x, and this here is the Fourier sine series of 1. That's a square wave. Okay, so now we have that if we want to set this sum of sines equal to this sum of sines, then each coefficient better be equal. So this coefficient b, c, n pi over L better be equal to 2 times 1 minus negative 1 to the n divided by n pi. So we equate these things. And what does that tell us? So now we know that, let's just write down that an, let's do both of these, an is equal to 4 times L over n pi cubed times 1 minus negative 1 to the n. And bn equals this guy. Then we have to multiply by L and divide by Cn pi. So bn is 2L times 1 minus negative 1 to the n. And now we have to divide by Cn squared pi squared. Okay, so now we have our final solution. So our particular solution that satisfies the boundary and initial conditions, boundary conditions and initial conditions, is u of xt equals the infinite sum from n equals 1 to infinity of an, which is 4 times L over n pi cubed times 1 minus negative 1 to the n times, what is that? Got to be careful, that's cosine. Cosine of Cn pi t over L plus, put a bracket here, plus bn, that's this, times sine, so that's 2L times 1 minus negative 1 to the n. Make sure that looks like a negative 1 over Cn squared pi squared times sine of Cn pi t over L. And then what comes after this is this term. This is sine of n pi x over L. Okay, so this is our final solution. Let me make several comments on this. First of all, notice that there's two frequencies here. So think of this as, you know, we have waves that are going to be traveling in general left and right. So one frequency is Cn pi over L. So that's proportional to C. You can think of C as describing like the tension of the string. So the tighter you pull the string, the faster this frequency. This is up and down. So each point here is going to be vibrating like this. And then this is going to represent a different type of frequency. This corresponds to the frequency laterally. The waves go, so the waves are going to be going left and right. So is this a sine wave, a sine of 2x wave, a sine of 3, whatever that is. So that frequency is embedded in here. So we have two distinctly different frequencies because one is based on time and the tension, and the other one is based on position. And finally, notice that the limit as t goes to infinity of u of x t is not going to exist. So the only difference between this and the heat equation is we had one fewer derivative, time derivative on the left. That gave us an exponential function, whereas having two derivatives gives us a sine wave. Or I should say a sine wave here. So exponential functions go to 0. They die out. Heat dissipates. Waves propagate. Sines and cosines propagate forever. So this limit does not exist. Now, if what we could do is if we wanted to have a wave that does dissipate, like it's waves do dissipate, that they lose energy, there's a damper, then what you would have to do is you would have to add some sort of k times ut term here. And that would give us, so that's something I think I will put on your homework, is adding extra terms like this. Okay, so that is the wave equation. That's the second of the big three two-variable PDEs that we've seen. We will see a variation of this in an upcoming lecture, a variation of the wave equation, which is called the Schrodinger equation. You probably know that that comes from quantum physics, and it's pretty much like the wave equation, except we have an imaginary constant I out in front of here. And there's a few other bells and whistles as well. So that is coming up next. And with that, we're going to leave it there.